My name is Sibil, and I am privileged to share something on a soft skill demo on mineral resource estimation, open pit optimization, design, and scheduling. And we are going to be using the GEOVIA product, Surpac, Whittle, and Minesched. Presentation, we'll go through something like this. The mineral resource estimation is a package from the resource concept, the database management, where we talk of database creation, linking, auditing. We'll do all modeling. We'll look at something on compositing and all analysis. Then we'll look at the statistical analysis. We'll come to the structural modeling, that's a variogram. Then we'll get down to resource block model and estimation. And we'll look at some validation tips if there's time. Then we'll look at something also on the mine planning aspect, where we'll look at some concepts in the resource, how you test and audit it. Maybe look at how to generate a modpath file. Then we'll look at how to build at least a cost model. We'll get some info on pit shell and optimization, a whole lot up to final pit selection. Then we'll look at the life of mine production scheduling. We'll also have some info. We'll discuss on how to improve maybe your MPV or CMO if there's time. And then we'll check something on the detailed pit design. The scheduling tool is also here, where we have the schedule initialization. We'll look at how to network your materials within different destinations. So material movement is here, targeting and blending, improving the schedule, and we have the short-term scheduling package. So this topic is actually a demo, so we'll do more of soft skill. I'm not going to bother you with theory, but we'll just have some few, we'll just look at something small, then I'll dive into the soft skill. But the whole thing is a workflow like this. We have data is taken, it is analyzed, then resource estimation, then it gets to the engineers and it is completed there. Take, for example, a drill holes like this. You have drill holes that have some samples inside them. That's the yellow portion. Anybody can come up with anything at all. For example, a very conservative geologist will end up with something like this because he doesn't want problems, and he is right. A very optimistic geologist can also come out with something like this. Then someone who is very extreme can also end up with something like this. The geophysicists can also interpret like this. And then we have the volcan guys can also come up with something like this. The open pit geologist may interpret it like this because he wants to take everything to the mill, and that's okay. But the conditional simulation guy will get in down and then also come out with something like this. So everybody is right in resource estimation. Well, all models are wrong, but some are useful, says one professor. So the mining engineer at the end takes the information from the geologist and he comes out, he designs something like this from the same drill holes. So whatever comes in from the geologist goes through the model network, and at the end, a pit will be designed based on what is given to the engineers. So the whole thing emanates from samples. And the samples, for resource side, you may have samples taken at regular or irregular intervals. And then because of that, we want to estimate. So we may have to do what composite, that's to just regularize or standardize at some standard interval, so that at least whatever we try to estimate, we are able to convince ourselves that we are doing the right thing. Then the whole thing, after modeling, will come to the compositing. After compositing, we'll go down to histogram. We'll look at the mathematical aspect, because you don't know what is inside the earth crust. And so you don't know what is inside the data until you take it or you throw it onto the microscope. And histogram is very good, able to tell you that, oh, okay, there are outliers or bimodal properties or all that inside your data. So outliers and what do you call it, bimodalism, are some of the things that trouble our resource data. And for that matter, we always have to try to, what do you call it, remove the outliers or use some Saska, what do you call it, top cutting analysis and all those things in order to trim the data, in order for us to get it into maybe variogram and all those things. So we have, what do you call it, a bimodal property here. Please permit me to, yes, I'm trying to rush a bit so that we can get to what all of us, what the topic is. So we have something like this. So this one is just indicating some two peaks, meaning two masters, which means this data contains some bimodal properties. Okay, so in our analysis, we were able to look at the data, the skewness, does it skew to the right or to the left, and what is even the level of skewness. So we look at all those ones, then you are able to remove the outliers, and you can get something like this. When it is true, we'll come down to the structural model, the variogram, which is one of the things that is troubling many of us, because variograms are some kind of very difficult to predict, but it's okay with the GEOVIA tool. Yeah. A variogram, what is inside it is just, it's a graph of variance with distance. So, but what happens is that the variability comes from the first sample taken. When you take, what do you call it, different values coming from the same sample location or the same zero distance, then we say there's a nugget. And when this variability goes up to a level, a plateau, then we say it has reached the cell. And at where the cell is attained, that distance is correlated, and we have the range. So we say there is a range of continuity if you predict within here. Outside that, it's uncorrelated. So that is just by way of trying to explain what a nugget, cell, and range is. Isotropic or isotropic is where measurement in different directions give the same value. And when we assume that no, there are some kind of anisotropic properties inside, then we begin to look at the anisotropic behavior. We also have this is where we say measurement in different directions give different values, or different, what do you call it? Values are coming from different orientations. Okay. So we have an example of an isotropic case where a sample is at the centroid, and then you have the sample values, what do you call it? Space within this particular block. Now, these three samples, the value here times the distance from this sample to the centroid, plus this one times its value to the centroid, plus the value here times the distance to the centroid. Now, when you take this all over the distance, then you say you have the average value. Because it's simply the weight times the, what do you call it, the sample value, summation of that, and then you have this. But in anisotropic case, it's not like that, because you are going to take the distance and you are going to convert it into an anisotropic distance. And that is by multiplying the distance of the sample to the centroid divided, or you multiply it by the anisotropic ratio. And whatever value you get becomes the weight. Then you will apply it in order to come out with the values. Okay, just rushing. So in a variogram, we have what we call the azimuth, the plunge, the spread limit, the lag. Maybe I'll explain this when we are using the software. Okay, so we have variogram. This is just a picture showing a variogram mapping where these are the different various structures one is trying to model. So every variogram that we pick at the end, we're able to locate the strike of mineralization when we think that this is where the continuity is. For example, you can see that these are all variogram fans and it is 360. So if this is your azimuth 0 down up to 360. Now, a variogram here may be 11.5 degrees. A variogram direction here may be 22.5 or 45. These are all variogram directions. Now, wherever I able to, what do you call it, analyze, then I come out, okay, the strike is through this. Then I can say that, okay, my variogram direction is along this side. So we have the spread, which is very important in variogram modeling because the spread will tell you the angle that your Okay. Hello, sir. Someone is requesting information from me.
Yeah, Samuel, you can go ahead. We'll address all the questions and suggestions after the presentation.
Okay, someone is requesting a recording. Okay. Okay, so I've allowed recording. Okay, so we have what do you call it? The variogram. The spread parameters are here, where we have the spread angle, which is always in line with the vector direction or the search line. This is the azimuth or the search line. Okay. So the whole thing about variogram in Surpac is very simple. You look for the strike of mineralization, which is the primary variogram. Then you look for the dip of mineralization, which is perpendicular to the strike. Then you look for the plunge of mineralization, which also inclines to both the dip and the strike. And that is how to come out with your major, semi-major, and minor ratios. Okay, so block modeling is simply trying to distribute your ore into various blocks. That's all, the ore body into various blocks. And a rule of thumb is that you have at least whatever the drill hole spacing is. If you don't have any information for a very new place, try to make sure you don't go at least less than 1/4 of the average drill hole interval. And that is okay. And the height would be at least information given to you as a geologist. What would be the bench height? Or depending on your mining flitch or your flitch height, you can also use that to get your block size. According to the mining laws, we also have something concerning block sizes. Yes, in regulation 88, subregulation 1 and 2, we have information there concerning bench height. And so usually our pit here, we make sure we don't mine more than 20 meters in height for a minimum a width less than 5 meters. Okay, so we have a lot of methods that we are going to we have in Surpac. A lot of them we have inverse distance, weighting, nearest neighbor, ordinary kriging, but now we are all using kriging. So the kriging, we have a lot of them in the GeoVia library, where you can get information. All of them, the Gaussian, they are all there. Okay. So all this at the end is just to establish a model, and then at the end, the geologist will come out and say, okay, this is inferred, indicated, measured based on the level of geological information that they've gotten with the environmental factors, the metallurgical, economic, marketing, everything will come out that, okay, even though it is inferred, indicated, or measured, we can even go for say, okay, this is probable and this is proven. And this information is important for pit optimization. So you can come up with something like this, and that is it for just the resource estimation. We will have a question later. Pit optimization is simply incorporating the work of exploration, the objective of the company. You bring in the risk analysis, the project scoping, scheduling, and then we have sensitivity analysis. These are all incorporating inside when you are doing your optimization. Okay, and what is it? We have an ore body here, which is from the resource guys. Then our aim is to get the ultimate pit design. We do our long-term schedule, we apply the cutoff, we have the short-term, and then that is what we say, okay, so the reserve. So from resource to reserve is the mining guys who take the resource and convert it into reserve for us. Then it goes back to grade control and the whole thing continues again. Okay. But what are some of the factors that affect pit optimization? Geological uncertainties are all here. The limit of mineralization, the grade, distribution, the faulting, joint, all these things, they are all affecting, they are all uncertainties. Economic issues are here, interest rate, inflation, power cost, capital cost, all these things also have effect. And then we have the parameters that are very key. The technical ones is that the geotech information, the tonnage and the grade from the geologist, dilution, recovery, mine recovery, mill recovery, rock properties, all these things, the continuities, the mining method, the production rate, and the economic parameters, very important for optimization. You have to consider the discount rate, the mining cost, processing and overhead costs, all these things, commodity prices, and all those are also important. So the whole thing that becomes an economic model has to get information from the geologist who provide the tons, grade, and rock type. Geotech guys will provide the slope information. We have the mining guys also coming in with the cost, whether implicit or explicit. They're all selection. Are they using cutoff, cash flow, value mode, or profit mode, whatever. The dilution and then recovery. Then we come to the financial guys. You have to have information about the metal price, discount rate, corporate objective. So what's the objective? Is it to increase MPV, or is it mine life, want to extend mine, or what is the objective? Or you want to even protect shareholders, whatever. We have information like that. And then the metallurgy also will provide recovery, cost, processing rate, and cutoff rate. So all these things are inside the model before it is qualified to be an economic model. Yeah, the whole thing is to get the pit, but what happens, some people mine, at the end, your pit will be a small pit or a larger pit. It depends on 3 factors: price, cost, and slope. So let price be good. When price is very bad, you end up with a small pit because cost is high. The same thing happens when price is good. Now, from here, you are going to end up with a very large pit because cost will automatically go down. But when price is good, even low grade and extreme low grade stockpiles and all those things that were redundant will even now be sold and will be sent to, will be used for they will all become when you have low grade stocks and all those things will now be taken because price is now good. We now increase, we go to increase the pay size, because you now mine at steeper slopes and you do more cutbacks. So you end up with a very large pit. Okay, in Whittle, we have a lot of methods. We have about 3 and so other engines are there. We have the floating cone, but it's no longer, this is a traditional method. So what we have in Whittle, we have like Grossman, we have pseudo flow, and then in fact, there are even some new engines that they are still building with improvement in AI. And what is important, we are going to use LG because it works with block values, it works with block mining precedences, and it's able to work with a 3D, a 3D outline with the highest possible value. Let me minimize this. Okay, so the first thing, after you get your model into Whittle is to check on the slopes. For example, if you have this, we use structure acts to do that. If pit A is mined, it means B has been mined, straightforward. But if B is mined, it doesn't mean A is mined. Yeah, and that is because we mine from top down, though we design bottom up. Yes, we have others who also, we have other methods that you can design from top bottom, but most of the time design bottom up. Okay. So what controls is that you want to establish a slope and you have a desired slope, but after generating your, what do you call it? Structure act, what happens is that you may not get the desired slope. So the discrepancy between this and the desired slope is what we call the slope error, or some people call it the slope accuracy. Anyway, so if a pit like this, let's say on a plan view, this is a pit, and you want to assign the various slope parameters. So for a bearing of 20, because if this is what we call it, the true north, measure from the true north to this, we are going to get 20, and that is the slope angle. Yeah, from the true north to this, we give you 77, and that is a what do you call it, 38. Then from the true north down to this place, we are going to have 135. So it goes in that order. Now in slope application, what happens is that we have, when the slope is constant, for example, it is increasing from 55 to 60. So you see the line is broken. Yeah, but where it is constant, you see that the line is solid. So we can have constant slope, or we can also have interpolated ones. Okay. And this is usually one of the formulas we use to calculate the slope generation for benches. The next thing important is the block value calculation. We have profit. These are the basic things to get profit, and revenue minus cost. And it's coming from this. This one will give you. So we have ore and grade giving you the metal times recovery, price minus the cost of selling. Then you have ore times the cost of processing. If it is ore, then the rock times the cost of mining it as waste. And that is it for the block value. It is also incorporated inside. We have all the terminologies here. Let's take, for example, this is a production scenario. You have a truck, and this truck you want to buy or assign it to a particular task. What will you do? You have a 50 bucket truck. It's taking 50 tons of 2 grams per ton gold. Another one has 100 tons. It can also take 100 tons of 1 gram per ton gold. Then we have the 151, which is taking 0.5% copper and then 0.25 gram per ton gold. Now the issue is which of this truck is weight assigning and where? Okay, so you put it into that equation. You have the grade times the tonnage, 50 times recovery, which is 92.5, multiplied by the metal price, okay, minus the truck load times the cost of processing it, minus truck load times the cost of mining it as waste. Now, this will give you revenue. This will give you the cost component. At the end, this truck, anytime you move it, this is what you get. Okay. We have another truck here, the 100-ton truck. Look at what happens. Grade is also here, 1 times the truck load times recovery. The same thing goes into that. And at the end, you have the same revenue minus the cost component here. At the end, anytime you assign this truck, yes, you are going to lose more dollars. Now, the issue is that what do you do with the truck? So you get more money. I'm not going to ask a lot of questions. Okay, so for the 151, it's okay, but we're going to compare the first 2 scenarios. What happens? It's very simple. It's because of where you are sending the truck. Because if the truck has a very big bucket and use it for low grade, yeah, the cost is coming from processing. So the issue is here. Yeah, it means this track is not good to carry waste. Ore. So you have to use it for waste. So that's why it's always good for bigger bucket to be sent for cutback and all those things to take waste. Yeah, so if you use that same track, look at what happens. Yeah. Okay. Okay. I've already taken that slide. Okay, it's here. So if you use the track, what happens is that you won't pay for cost of processing. You only pay for mining. What happens at the end? You have more money. Yeah. So that is just a simple scenario from production that you can take it. So what happens is because whenever the cost of processing is higher than the revenue, you have to treat the track load as waste and then be free. Okay. And it's coming from this. Marginal cutoff has a lot of influence on that. You have the cost P over recovery times price. Okay. Dilution and recovery should also be factored in, and block size, minimum mining width, all of them will play a role when you are talking of dilution and what do you call it, all loss. So over here we are losing, and inside here we are adding more weight. So we'll talk on that. There's no time, let me just rush through. So the cost, there are three main costs or time costs. We have mining, processing, and selling. And the mining cost is very simple. Any cost that or any expenses that will continue when mining stops, it means it was not a mining cost. So you check at your place, if any cost continues when mining stops, that cost was not coming from mining. The same goes to processing and then the selling. Okay. We can also do something about the MCAF, or the mining cost adjustment factors are also important, and it has to do with the reference mining block. Yeah, we used to calculate the cost adjustment factors, and some people call it the base case mining. In fact, it does not physically exist, yes, but it's very, very important, because without it, it's very difficult to adjust your cost down the levels. So it's a very important thing that you should also take note. These are the rules involved. One, that the value must be calculated on the assumption that the block has already been uncovered. Yes. And also, you also have to assume that the block will be mined. And number three, there must also be an assumption that any expenditure that stops if mining stops should be included. The same for processing and selling. And rule number 4 is that you shouldn't be biased. Okay. So the whole thing about the block value formula is there. This is something we have all been doing. Picture, very, very important. So it has to do with, we have the revenue factors, or some call it the RFs. And at the end, you have something like this. So what happens is that there will always be an inner pit, because if you are generating a lot of pictures from a number of, or a series of factors, revenue factors, what happens is that you end up having what we call an inner pit, intermediate, or whatever. You choose what your inner pit is. The inner pit are important because they help you to know where to start mining. The intermediate pit are very good also for, what do you call it, sequencing, and also choosing pushbacks. Some are also very good, yeah, to help you, even if you are, what do you call it, checking interim pushbacks and all those things. And then the pits which have RF of 1 or near 1 are also good to help you check what is happening today. So sensitivity analysis and risk analysis are also performed around here. Then the outer pit, very important. You may never mine it. There are a lot of pits that were optimized over whatever 50 years ago. They've never mined the outer pit, yes, but it was important, because without it, you wouldn't know where to sit your magazine, your plant, your infrastructure, mine office, and all those things. Yeah. Now, revenue factors are coming from something like this. If, for example, today's price is $1,100 per ounce, and it means that's RF of 1. And if you say we have 0.5, then it means half of it. And 2 means twice of it. So it's very simple. Okay, I'll just get down. Scheduling or sequencing, you can start from your, what do you call it? The aim is to mine the pit in red, but someone can say, okay, I want to mine pit 1, 2, 3, 4 before I get there. That's a mining method. Another person will mine the first pit shell, mine from here to here to here. So he's mining 1, 3, and 5. That's also, what do you call it? A sequencing method that is used. They are all, what do you call it, ways of mining. Or selection method, very important. You can choose cash flow, cutoff, whatever. You can, the software also allows all that. You can use whatever method that you want. Okay, production limited by mining. Simple. It means anytime we mine a block, life of mine has been extended. That's simple. It means production is limited by mining. But when production is limited by processing, what it means is that it is only when an ore block is mined that extend the life of mine. So when an ore is mined, the life of the mine is extended. And we have some companies where production is not limited by mining. Mining engineers are not controlling it. They are not controlling, processing guys are not controlling, but it is controlled by the sales guy. So we have some companies where they are dealing with those industrial, yeah, very, very important. When we don't sell, it means, so you can even stop mining, but the life of mine will still extend because we base our limit by sales and not by whether you mine or process. Okay. So at the end, we have something like this and that. The scheduling, we have the worst case, the best case, the specified case. One is mine top down, another one mine pit by pit, another one, okay, pick the feasible domains and like the specified. So it's able to schedule between the worst case and the best case. Simply, worst case is simply trying to mine, but you reserve the MPV to the end of my life. The best case here, you mine, but MPV is reserved. Sorry, the best case, what do you call it? The MPV is mined, or the MPV is brought to, what do you call it? Front. So we say it is best because it ends with the best MPV. This is worst because it reserves the MPV to the end of mine life. That's what. Well, this is very practical, very easy to mine. This method, you may get to a place and you get, what do you call it, trouble because if the pit closes up, you have to go back and do cut back again and all that. So it's always good to see if you can get a pit which will make good use of the two of them. So we say skin analysis and all those things is coming in here. Well, we may not, just trying to rush through the slide. Okay. So all those methods are here. And then you can get something like this, and then you do your step. Okay, so let me just move to, let me open it, the two. So for example, if you have, starting with a resource, if you have something like this, let's say a database, like this, yeah, yes, I have a lot of, what do you call it? Live data, or live mine data, for, what do you call it? Other informations or confidentiality sake, we'll use some unknown, what do you call it, training data just to check certain things. So if you have something like this, drill holes, you first, you have your color information, and then you have your color, your survey, all those tables, then you generate the database. Can I do something? The Zoom is covering, okay. Okay, I'll do that. So you have something like this. What happens? So you first have to go to database, database. So then you open and you create a new database. Then you go there again and import. So when that is done, then you can have drill holes like this. So the next thing is for you to assign or apply the drill hole color styles. So you come to the down there, maybe what is important is the assay. So for example, gold values, you assign the ranges. Then we have the geology, where you can also look into what are the various rock types. So when you do that, it makes it easy to interpret what is inside the data. So if I now come here and I go to geology and I'm putting the geology labels, let's say rock, let's say with width of 2, and then I have the labels, I can come and apply my assay, and then my geology here. And if I assign this info, maybe the geology go to left, for example, then the offset, I can make the assay maybe 3, then I place the geology maybe 4 point something. So if I do this, it's easy for me to section. You can use, we have a lot of them, any of them you can use. So for example, if I go this way, or let me just increase the space. So we have this. So if I run, you'll be able to interpret what is there. So from here, you now go and you digitize. So we say you are wireframing or just the delineation. So when you are from here, you're able to digitize. And then, so if you're able to digitize, for example, let me just show something like this. So you will see that what you have done, whether it is correct or not. So if we delineate like this, yeah, these are all ways of delineating. So when you are done with these wireframes, you go ahead and then you model. Very simple. You go ahead and then you model. So after modeling, then the ore body, for the modeling, you go to solid and then triangulate, and then you run the modeling. When you are done, then it's good that you go straight and then you composite, because the composite is what will extract, it's a way of extracting the samples in the database for us, but this time with equal intervals to help you know. So we have different compositing length and all these things you can use based on. So this is it. So you do your compositing, and that one too, you can find that in the database, you do there and do your compositing. So what do you call it? If you come to composite and all, you can use either downhole, usually good for downhole if you are dealing with what do you call it? Downhole samples, and we also have bench samples for break control and those things. So then after that, you apply the statistical what do you call it? Analysis. That is, you do the histogram. So for example, if you come to analyze, because you can get basic statistics here. The histogram is important because without it, we will not be able to know, because without this one, we won't be able to know whether there are outliers or whatever inside. Okay, for time's sake, I'll just run through this. So when you do your statistical analysis and you get the top cut, then you apply the top cut. You can use a string math tool to do that. So you can use this to apply a top cut. Okay, go and bring the sample, then you indicate the new value, the new name, then you apply it, and then you get the top cut value. You can use any of the if analysis questions, like let's say if sample A or the sample or goal value is, let's say, less than this or more than this, give me this or that, and it will give you the top cut. Then from there, you can go ahead and then apply the, what do you call it, take it to variogram. So the variogram analysis, So you can use any of these two to do that. So let me just use this for example to show the variogram. So first thing is to at least do the downhole variogram. That is to help you establish a nugget. Then from the downhole variogram, you can now do the what do you call it? The directional variogram, where you can now have the primary variogram, secondary variogram, and all those things. So it's good you do that. So if I have something like this, it's a variogram. After doing the downhole variogram, I plot this, and then it helps me to be able to know what do you call it, whatever I've done. This one will help me to get the nugget seal and range, and then I will now go to variogram mapping in order to get the what do you call it, the anisotropic parameters. That is the variogram along axis. So that one will give me the major, minor, then semi-major, all of them. Because I need them, because if I'm going to do Kragen is a parametric estimator, and it depends on variogram parameters to do that. So once you are through, you are good to go to block modeling. You are good to go, and then you quickly run a block model. Okay, for example, so block modeling, you just pick something, let's say something like this, new, then you give it a name, whatever it is, you give it a name, then you enter your, what do you call it, the coordinate constraint, or you can pick, what do you call it, the file from whatever you already have. Yeah, so let me just make this one my, so if so because of time, maybe questions will come. So if I do something like this, this is a model. Okay. So this is a block model, which, what do you call it, we've done, for example. So all you need to do is you have to add the attribute and all those. So you go into, you add the attribute, then what do you call it, you do your constraining for the all domains. So once you are through, then you can, what do you call it, do your estimation. And you can also see that from the same block modeling, you can go there, ordinary Kragen inverse distance, any of them, run your estimation. And when you are through, so we have parameters, for example, like this, we have a lot of them. Well, these are all attributes you can see. So for this is low value estimation for IDW, and then all those things. So if I am looking for any of it, so I only need to go to constraint and all that, then I will maybe do a constraint for whichever I'm dealing with. So for example, I go into, okay, I want to see the goal value for say, what do you call it? So I want to see the grade. So maybe with a certain cutoff or whatever I'm dealing with. So I can have this. This will show me the ore body. So the two domains are here. And then from there, I can go in to do whatever I want to do with them. So maybe you want to scan, you want to see what. You can do all that. Once this is done, the resource guy will go ahead and then do his validation section. We have a lot of validation. We have the trend analysis method. We have a lot of them. You can use a variogram validation method. You can use a SWOT plot. You can use a lot of them. So you do your validation, you do your report. You go into the block model, then you run the report, and you are done with your work. So you pass the model straight to the mining engineer. The mining engineer takes it, and then he deletes some of the attributes that are not important. And then what is important is the tonnage, the tons. That's the grade, the density, and then the rock types. Or if you have used some geological zones, like, or you have already classified into what you call it, whatever, and you want to optimize using what you have. So what is important is that then I build my mod file from here. Then I'm now talking as a mining engineer. So I build my mod file from there. Then I just take it to the economic software. That is the Whittle. And I go there and do my optimization. So if, for example, you come Whittle to the same thing, you have a new something like that, then you build start your model here, for example. So if I have something like this, I build my project, I go to add, and then I go and pick the mod file I have created, for example. Then I am able to I have 10 minutes more. So I'm able to what do you call it? Then I'm through. I have this. Then you now go ahead with the slope input. You put your slope and all. But before you come to slope, you had already dealt with mining, cost adjustment factors, processing. You dealt with your slope. You can do that in Surpac, or you can come and do those things in Whittle. Either way, yeah, you can do whichever. You can do all those things using the assigned value and all. You can do those coding in Surpac, or you come to Whittle, and then you can also enter those things here. So whichever way. So this is just a demonstration. So you go through that. This is your block model. You look at the dimension. You come to the format. Look at it. You change the units to the required or the desired unit. Then if so. Whatever. So the metal, are you dealing with it in ounce, or you are using what do you call it, gram, or what? So whatever unit it is, you look at all those things. You enter those information. You look at even what you have exported, the tonnage. Yeah. So you have exported fresh, trans, or whatever. You look at the information and cross-check with your resource model, what the geologist gave you. So you cross-check this information just to have information about what is happening. Then you can now go ahead. If there's a need for you to do reblocking, sometimes you've seen that maybe you need to change the block size, because the geologist may estimated using larger block size, and you now want to optimize with different block size. You can do that by at least going there and then doing reblocking. So you can do reblocking, and at the end, all these things will come under the reblocked block model. Then you can now continue from there. So because of time, I'll just go back to this, and then we'll just so let me see the model new. Okay, let me see. So let me save this one, and then okay. So this is an example of something. So you have the slope, and you come here, you have the slope, you go to the slope profile, and you enter the various slopes. So what geotech advised you? So this one was actually a very complex slope information. We have different rock types, and given we had different 4 domains, and each domain we had what we call 4 slope what we call directions. So you can see the slope angle and the variance. So all these informations, you have to enter them, and then you go to the page shell, and you enter your reference mining cost. Make sure you know what you are dealing with. We're actually dealing with per ton. So you convert it. If the information you had is in BC, you can convert to per ton here and deal with that. You enter your minor recovery and then dilution, if you have those things to apply. So here we have 5% all loss, and then we have 10% dilution. Then the mining cost adjustment factor. So you see the MCAF equation it's a range function, and you can actually do that using Excel to generate what do you call it, a straight line graph equation. And that equation is what you are going to use. So if you see this, you apply it to the benches based on the information that is given you. Okay, and when you are through, then you go to the processing node and also apply your processing cost, recovery, and all those things. Go to the metal. Here is very, very important. The price, you put it, yes, but it depends on whether you have other things that are proportional to the price. For example, royalty, anytime you what do you call it? You sell, you pay. So you have to factor it. You can factor royalty here. You can guess the percentage, let's say 1% or 2% of this. You just make sure you take it from here, or you can add it to the cell, depending on whatever. And you go down and do your optimization. So if you are able to go through that, it's asking me, I'm going to run this. So if you go through that, you can see your pit. While this one is running, let me quickly go to the operational scenario. I'm trying to be fast to show something. Okay, so at the end, you generate your pit shells. They are here. And then let's see, I have this pit. So at the end, you have this, and you try to check whether your pit will hit the model if after design. So you check. So you can just display the topo to see, yeah, yes, you have information about it. And whatever it is, so we have the info. So you can come to the info. Okay, I want to invert. You can display any other information and the block survey. So, how is this? So you can display whatever it is. For example, you want to display the grade or whatever, P curve or whatever, you can display all of them. So if, for example, you want to display the P curve, you just come and see what you want to display. If you want to display whatever, the grow value, that's the most important thing. So you can display and see how the gold value. So this is just a graphical view. Then the most important thing for the picture. So you have the various pictures here generated using so you have the pit. These are the revenue factors. And then we have the waste for each pit. So if I'm mining pit 4, for example, this is all the strip ratio and all those things. Now, if I'm choosing starter pit, which one will be my starter pit? A lot of factors are involved. Which one will be my pushback choosers? A lot of factors are involved. Which one will be my final pit? A lot of factors are involved. You can't use only this one to determine that. You have to bring in the time issues. That's the operational scenario where you are now going to see the clock. You see the clock is now running. This is where you can make a lot of changes, whatever. So this one involves time. When I bring in that one, because this one will now work with limit, mining capacity, processing limit, all those things. So if I bring in all those things, I will be able to come up with pit by pit graph, which will also help me now to see what to do and which pit to choose as my starter, what final practical choosers, in that order to a lot. Okay, so if at the end we do this and we come out with the final page, you've done your scheduling, you can do a lot of scheduling, take a lot of scenarios into concern. Okay, so you do a lot of scheduling. At the end, then I choose my pit. Let's say pit 36 becomes my final pit. So I only have to come and see how I can design that pit shell. So I bring it, I export to Surpac, then I come quickly. Where can you find this? Okay, so I have, so this is the pit. Yes. So for example, this is now my pit. Okay, the pit is here. So this is now my weighted model or my pit model. So this is different. So over here, then I look for where your final pit is. So for example, this is the final pit. Let's say this is the final pit. So using constraint, you can get the final pit because when you come to this summary, we have a lot of them. We have all of them are here. the MCAV, the pit numbers, all of them are here. That is from the picture node. Then with this, you can see you want to see your pushback and all those things. You get to you use the mining sequence model. So let me rather bring the mining sequence model, which for example is this. So if this is my mining sequence model, I want to see what is inside this, for example. So I have this, and I want to see my pushbacks, for example. So these are my pushbacks. So based on this, let me bring in the final pit to see. Okay, so I can see a lot of, because I've not brought the topo, that is why you see all these air blocks just on top. So, okay. So we have to do this, and then you export this pit, or you can just from Whittle, you could have just brought the picture in a form of a DSL file, and you could actually use the DSL file to do that, just to do your design. So if I had brought it as a DSL file, you see that this is the picture as a DSL file, then I'll just take this one, I'll section it, and then make sure I also take the ore body or the ore blocks. I also make sure I section them. And then if I'm able to do that, so if you do that, this is your ore body. Now this one is now for what is this is your reserve, because this is what is inside the pit per the picture. In fact, there were some outside, but it has been cut so that we have this one. This is what I will now use, and then I'll go and do my design. So for the pit design, the Whittle will give you overall slope angle. You make sure you go to pit design, and before you do that, you have to convert that overall slope angle to the design angle, because they are not the same. So you have to make sure you put everything in, let's say, whether it is coming from block model, you choose block model, or you are going to use design slope, you do that. Then you come to, what do you call it? You set your gradient, whatever it is, you put the angle. You can do that. Or you just go straight to expand and use the multiple bench system. So over here, it will ask you to actually tell where your base pit is. You have to actually indicate that. Yeah. So let me put everything on plan view. So it will ask you for your base pit. So based on this, if I have something like this as my base pit, this is what I'll use to design up. So I'll make sure I go to design, slope method, put it on that view. Then I come to design, then go there again. And then I will now go use the expand this, because I'm converting. I want to convert. So if I just choose something like this, I want to convert from the Whittle. A lot of engineers use Excel for this, converting from this. A lot of Excels are, yeah, but you can also do that simply using the software. So for example, you use auto height, for example, you just indicate the number of benches you are going to mine. So if it is, let's say 12 benches, for example, or 21 benches, then what would be your slope angle? You put it there, you just put something there, but we don't know for now. And then your bench height, let's say it is 10, and then your bend width. So automatically you see the overall slope angle here. So you now have to do adjustment. You do a lot of iterations in order to get. So if Whittle angle was, let's say 40, you have to make sure you get a 40. Okay. So that is how you go about that one. And when you are through quickly. I need 5 minutes to complete this. Okay. So remove. So when I am done, there are a lot of things you can check with whether material mining year 1, mining year 2, material sent to the mill, fresh material sent to mill, fresh material sent to. You can check all the using constraints. Maybe material mining year 2, you see what will be mining year 2. All those things you can do all that. Then when we are through, again, we will now take the model, the result model. Then we will now just export the material attribute to Minesched. So you take it to Minesched. What are you going to do there? What is important if you're going to Minesched is that you should get the material classes. Very, very important. Once you define the material classes with your your topo, your page, those are the parameters you need. And so for Minesched, what is important, what you need to do is that make sure you have these parameters before you go into Minesched. You should have the block model, you should have the GTM, that's the topo, the pit, or the DOM, all those things, you have them. You should have the, haulage. Yeah, you can digitize it in the pit and all those things. Have your haulage route and all those, you can do that. Then the polygons. So if that's for short-term scheduling, we have long-term scheduling in Minesched where you do a lot of things. But if you want to do short-term, just a bench kind of mining, you just get your polygon, for example. And then once you digitize the polygon, use the polygon, and then you get into Minesched. And you can just go to that. So now, if you walk into Minesched, you get the first thing to define the geology, where you have the model. So make sure, so you go here, you go to add, and then you bring the model. Once you bring it, you make sure you validate it. So when you validate, all the information will come. A lot of engineers don't like Minesched because of this. You see this? Yeah, because Minesched, if you don't do the right thing, Minesched will not allow you. Yes, but I like Minesched because if you can obey all the rules, you always have a sweet gem. So you always be able. So you see a material class attribute must be defined to generate a material report for block So I'm supposed to go and generate a material class attribute for that block model before I can use it. That's what we say. So make sure you define that, then you go to your schedule, and then the surfaces. This is where you are going to enter all your surface, the equipment are going to come here, your location, your mining locations, your destinations, and then you bring in the resources and you state all their capacity, the mining method. Are you mining by polygon, benches, all those things, you state them, mining direction. Then you do the material movement, how you are going to flow the material. You're going to flow pit A or pit B to where, all those things. Then you can go ahead into mining, and then you also add in the resources and their capacity and everything, the parameters. Then when you are through, yeah, you can add calendars to your schedule. Yeah, you can add calendars. We have calendars, different. At the end, then you go to your schedule, and then you go and run the schedule. For the schedule, this is where you determine whether you are doing short-term or long-term schedule or all those things. It depends. If it is year and above, you can state it here, or monthly, semi-annually, or that to hourly. So you state your epoch down to the period, all of them. So for example, this one was just for a year. So in weekly, 52 weeks. So it's a small project, very small. So at the end, you just get something like this. Remember, these surfaces were designed. That is the topo and order you are seeing. So you must have all those ones to apply the constraints in Minesched. Yeah. And when you go through that, you'll be successful. The time. Okay, so I'll end here for if there's any question.